Lecture number 12, combined cycle, and we will be doing some example of the combined cycle. Start with the example 8.4 and example 8.4 of Al-Wakil, power plant technology by Al-Wakil. The combined cycle as shown in figure 8.20. Now we have already discussed the combined cycle. With the supplementary firing as a gas turbine fuel represented by 6 CH2.145. Air fuel ratio corresponding to 400% theoretical air. Gas turbine inlet temperature is 2600 degree Rankine. The pressure ratio is 8 and polytropic efficiency of 0.9. Supplementary firing using the same fuel raises the gas temperature to 2000 degree Rankine before entering into HRB. The gas leaves the stack at 800 degree Rankine cycle, 800 degree Rankine temperature. Steam is generated at 1200 psi and 1560 degree Rankine from a feed water which has got the temperature of 780 degree Rankine. Calculate the heat added in the supplementary firing in BTU per pound mass of the gas and the air mass ratio of airflow to the steam flow. So in this example, we do have got two cycles. One is the gas cycle and one is the Rankine cycle. So drawing a little bit sketch of the uh, schematic diagram of the cycle. So it's say like we do have like the inlet of the turbine, the gas turbine is given. So inlet of the gas turbine is there and exit of the gas turbine is given. So inlet of the gas turbine is at 2600 degree Rankine and exiting it at, oh sorry, exit temperature is not given. So we do have got like the pressure ratio which is 8 and the polytropic efficiency of the turbine is 0.9, while the polytropic efficiency for the cycle is given, which means like it is the polytropic efficiency of the turbine as well as the compressor. Supplementary firing using the same fuel raises the gas temperature to 2000 degree Rankine before it enters the HRB. So that means like after exiting from the turbine, gas turbine, there is a supplementary firing, and that is actually in a heat exchange, a supplementary firing using the same fuel that raised the temperature at 2000 degree Rankine. So we have got a supplementary firing over here. Then that supplementary firing, and then after supplementary firing, it is entered into heat recovery boiler, which is HRB over here. And then from the HRB further, it will be added in a steam cycle and obviously to the generation of the steam, which is steam is generated at 1200 psi and 15 from the feed water, which is at the inlet is 780 degree Rankine. Calculate the heat added in the supplementary firing over here and the mass ratio of airflow to the steam flow. So first thing, like if I would just complete the schematic diagram, so that would be combustion chamber over here, and then we do have like inlet of the compressor and the exit of the compressor. So starting from the compressor inlet, we have state 1, state 2, we have the inlet of the turbine at state 3, then exit of the turbine at, let's suppose, state 4, then at exit of the supplementary firing at state 5, exit of the HRB from the gas cycle is state 6, and let it be at inlet of the feed water inlet it at state 7, and actually the exit would be, let's suppose, state 8. So that means like a little bit of the numbering to in my cycle. This would be same as somewhere here. If I draw the TS diagram of gas cycle, so the gas cycle would be, an inlet would be at state 1 and exiting of the compressor state 2. Make sure like the compressor, as I said earlier, it is not isentropic compression but a polytropic efficiency of 0.9. Then also for the turbine, it is not isentropic expansion but a polytropic expansion towards another enthalpy, which entropy, which would be increased. Now exiting at the turbine exit, gas turbine exit, we would be adding heat into the supplementary firing. So from 4 to 5, the temperature would be raised and entropy would be increased, and there would be actually a heat added into supplementary firing. Now that supplementary firing heat, when it is added, it is further enter into before entering into HRB. So that means like this one is 200-degree Rankine over here, and this is 2600-degree Rankine. Now this from 5, it will be enter into HRB, and it will be exiting the HRB at zero point 0.6 at 800-degree Rankine. Now that's the part where we are entering into the HRB. Sorry, exiting into the from the gas turbine cycle and entering into the steam cycle. Now the steam is generated at 1200 psi, and which mean like the steam would be at over here would be at 1200 psi and a temperature of 1560 degrees degree Rankine, and over here at this point, which is at 7 somewhere, we would be having a feed water temperature of 780-degree Rankine. Now moving forward, the point would be like to find the heat added in the supplementary firing and the ratio of the airflow to the steam flow. So if I'm looking at this diagram and further the TS diagram, so the heat added in the supplementary firing would be from 4 to 5. So I need to find the enthalpy at 4 and enthalpy at 5 as well. If I'm looking at the mass ratio of airflow and the steam flow, then I'm looking at the enthalpy of 5, 6, which is actually in a gas cycle, and further I'm looking enthalpy at 7 and 8, which is actually at the steam cycle. But looking for the enthalpy at 4, I do not have got any information given. The only information in this point is that I have got the pressure ratio, which is at 8, and I have got the polytropic efficiency, which is of 0.9, which is 90%. Yes, I already know the fuel ratio, air fuel ratio, which is 400% theoretical air, and I'll also know that it is actually a fuel which is actually CH 2.145. Now, in this point, what I would need to do is actually either I would use the ideal gas equations or either I would use the A table, which actually is available in Alwaki. If I'm using ideal gas equation, so ideal gas equation would be not a perfect equation for this kind of an example, because the the gas which is entering is at 400% theoretical. So that means like the ideal gas equation is okay for the 100% theoretical air, but would not be good for 400% theoretical air. So for 100% theoretical air, I would be okay with using the ideal gas equations. But for 400% theoretical air, it will be difficult for using that equations. So further, what I would do, like I would use the A table, and the A table would be looking something like this. So going to Al-Wakil and A table from Al-Wakil. So if I look at the A table, that is my appendix I, and you would be actually finding the A table in Al-Wakil, book of Al-Wakil. So I have got the enthalpy and isentropic pressure ratio for dry air. So I have got the temperature, enthalpy, and the pressure ratio on which the either the compressor is working or either the turbine is working. So going towards the another table, let's say table number 2. So that would look like enthalpy and isentropic pressure ratio of the product of the combustion if I have got the AFR, which is 200% theoretical air. Then further down, if I'm looking at, it would be enthalpy and isentropic pressure ratio for the product of combustion if I have got a theoretical air of 400%. So in my example, I have got the theoretical air which is equal to 400%, and then I have got the inlet temperature which is equal to 2600 degree Rankine, and I've got the exit no, sorry, I do not have got the exit temperature given, but the inlet temperature is given, the pressure ratio is given. So I need to find the enthalpy if I would just look at it like this. uh, Going towards the question back. So I have got the temperature, inlet temperature of the turbine, gas turbine, which is 2600 degree Rankine. I've got the pressure ratio given, which is actually 8. So that, having said that, I would go to the steam table, sorry, air table. At 2600 degree Rankine, I would find the PR as well. And from that PR, I would just find the state at 4. So let's say going towards that one, at 2600 degree Rankine, temperature is over here. So 2600 degree Rankine, going further down there, not sorry, this one, that would be 2600 degree Rankine, which is actually at state 3. The enthalpy given is 19979.7 BTU per pound mole, and the pressure PR at that point is given as 586.4. So writing it down over here, I've got temperature at temperature 2600 degree Rankine. I can find a pressure which is PR at 3, which is actually 586.4, and enthalpy, which is over here. Now for the state 4, so PR pressure ratio is pressure ratio between 4 and 3 is given, which is PR3 by PR4 is given, which is equal to 8. Now PR3 we have already find from the steam table, sorry, from A table. This 8 is given, so we can find PR4 pressure at 4, which is 73.3. Now further going to in the A table and finding the value which is 73.3 now, and corresponding to that value we will find the temperature and the enthalpy. So going further to the A table, finding the value of 73.3. So if I would just look at this point, that is 73.51, and that is 71.66. So interpolating between them, roughly interpolating. So I would just say like roughly it would be 1578 something, and enthalpy would be further a little bit down there. So that means like interpolating between them, I can find the enthalpy and temperature at state 4. So that means like 1579 degree Rankine is there and enthalpy is over here as well. Please write down the value of enthalpy, unit of enthalpy, which is BTU per pound mole of the gas. Now that is the enthalpy, sorry, that is 4 rather than 3. So I find the enthalpy at 4, which is not 4 but 4s over here. So now putting that enthalpy in this value in this formula, and I can find enthalpy, actual enthalpy, which is would be enthalpy at 4, that is H3 minus H4 divided by H3 minus H4s, and I can find enthalpy, which is 12347.1 B2 per pound mole, and the temperature which would be 1685, corresponding to that enthalpy. Now going further to the next bit, it's a like now after 4 we would be having a supplementary firing which would raise the temperature of the gas from this temperature to 2000 degree Rankine. So going to 2000 degree Rankine, we have to add some fuel to it and we have to do some combustion. So when you are doing some combustion, so let's imagine like whatever what we have been given. Say if I've got 400% theoretical air over here, or if I would just say 400% theoretical air was here, and obviously there is actually the same theoretical air was over here as well. Now if I would just add fuel into the supplementary firing, there would be a combustion, and obviously 100% theoretical air would be utilized in a combustion if I'm looking at this stoichiometric equation. Now if the 100% theoretical air is utilized, so at state number 5 I would be left with 300% theoretical air. Now so that means at 2000 degree Rankine, if I'm looking at the enthalpy in the air table, I would be looking enthalpy at 300% theoretical air. So let's check this one, the air table. So that is enthalpy at 400%, but that is enthalpy at 200%. So that means I do not have got the enthalpy table of 300% theoretical air. So imagining like I would be further a little bit, or if I was assuming that at state 5 now, I've got the percent theoretical air as 200%, as there was a combustion as well, and there might be some other factor as well. So assumption would be based on like I do not have got the a table of 300%. If I do have, then I would be using that one as well. That one. So 200% theoretical air and a temperature of 2000 degree Rankine. So at 2000 degree Rankine, at 200% theoretical air, I would be having an enthalpy of 15274.5. Going back to the question, so at 2000 degree Rankine at 200% theoretical air, I've got the enthalpy at 15189.3. Let's check like if I would just uh, using the same thing. Then at 600% theoretical, 600, sorry, at state 6, 800 degree Rankine, I would be having an enthalpy, for in the same table, I would be having enthalpy of 5676.3. Let's check, sorry, again, I was a little bit confused about the value. Sorry, yes, the value is this one rather than the 210 one. So the value is of 200 and 2000 rather than 2010. So I'm having enthalpy of 2000 degree Rankine, and I'm having the enthalpy at 800 degree centigrade, sorry, 800 degree Rankine. So going further up there, 800, and that is enthalpy of air at 200% theoretical air. Now, this bit of the question is a little bit solved now, but the point is like it's written in the question that you have to find the heat added in the supplementary firing, which is actually from 4 to 5 in BTU per pound mass of the air. While you the in a question, sorry, in an answer, what you have done in a steam in an A table, what you have done, the answer is actually written in BTU per pound mole. So if it is BTU per pound mole, so what you have to do, like you have to multiply with the mole and divide with the mass. Excuse me. So you have to multiply with the mole and divide with the mass to convert it into BTU per pound mass. So that means like the number of mole of air uh, and the mass of the air. So that would be required if you want to solve the question, or if you want to change your unit into BTU per pound mole into BTU per pound mass. So I will left this thing as an exercise for you, but that exercise is based on the example 8.3. So in example 8.3, you have to go to the example and find the AFR ratio, which in there would be a schematic equation for combustion of CH 2.145 with the theoretical air and with the 200% theoretical air and also with 400% theoretical air. Finding that one, you can find the molar mass of 200% theoretical air and molar mass of 400% theoretical air. Now, if once you find the molar mass of 200% theoretical air and 400% theoretical air, multiplying this with the 400% theoretical air molar mass, sorry, not this one, the enthalpy, and multiplying these enthalpy with 200% theoretical air molar mass, you can convert these into the per BTU per pound mass. I'm leaving this as an exercise, and I hope like you will be doing it. Now going further to the next part, it say like calculate the heat added in supplementary firing. So that means like the heat added in the supplementary firing would be from H4, H5 minus H4, and that would be heat added from the supplementary fire. Now the heat added in HRB would be H5 minus H6, which would be here now. Now, once you have added the heat into the HRB, that heat is further utilized by the steam cycle to convert the feed water to the superheated steam. So that is also given, and that means like when the steam is exiting from the HRB, it is having a pressure of 1200 psi and a temperature of 1560 degree Rankine, while feed water inlet temperature is 780 degree Rankine, and definitely that would be in a saturated state, so and a liquid state. So just going to steam table, finding the enthalpy H6, sorry, H7 and H8. So you can find the feed water entering HRB and delta H for the steam enthalpy, feed water enthalpy. Just find the enthalpy change, then enthalpy change of this one. So that further would say like mg into H5 minus H6 divided by mv, which we have already done, into H7 minus H6, sorry, H8 minus H7. So once you have done that one, you will be finding the ratio of the ratio of the air into steam, which is already required. Now, moving to another example, an example 9.12, and that is example of Moran and Shapiro. Energy and exergy analysis of the combined cycle gas turbine vapor power plant. Um, we will be not doing the exergy analysis anyway. The combined cycle gas power plant, vapor gas power plant, has a net power output of 45 megawatts. Air entered the compressor of the gas turbine at 100 kPa and 300 Kelvin, which is the atmospheric condition, and is compressed to 1200 kPa. The isentropic efficiency of the compressor is 84%. The condition at the inlet to the turbine is 1200 kPa, 1400 Kelvin. Air expends through the turbine, which has got the isentropic efficiency of 88% to a pressure of 100 kPa. So back to the atmospheric pressure. The air then passes through an interconnecting heat recovery steam generator and finally discharged at 400 Kelvin. Steam entered the turbine of the vapor power cycle at 8 megapascal, 400 degrees centigrade, and expand to the condenser pressure of 8 kPa. Water entered the pump as saturated liquid at 8 kPa. The turbine and pump of the vapor power have the isentropic efficiency of 90 and 80% respectively. Determine the mass flow rate of air and steam, each in kilogram per second, the net power developed by the gas turbine and the vapor power cycle, each in megawatt, and the thermal efficiency. And obviously, as we are not doing the exergy analysis, so we are not supposed to do this thing. The combined vapor power cycle, so we have got the inlet condition, which is temperature 300 Kelvin, and the pressure is 100 kPa, which is 1 atm. Power plant operate at steady state with the known net power, and obviously the other condition are known. So turbine compressor pump efficiency are also given. So we have known the uh, volume control volume condition anyway. Now let's say inlet of the turbine is 300 Kelvin, 100 kPa. The question is over here again. We have got the isentropic efficiency of 84% of the turbine of the compressor. Then it is actually in a combustion chamber, and inlet of the turbine is 1400 Kelvin, and the pressure is 1200 kPa. So this pressure, as it is constant, so it is the pressure at inlet of the combustion chamber as well. We have got the efficiency of the turbine as 88%. Then we have got the inlet of the HRB, and exit of the HRB is also known, which is 400 Kelvin, and temperature and the uh, pressure of 100 kPa. We do have got the inlet of the turbine, the steam turbine, which is 400 degrees centigrade and 8 megapascal with the efficiency of 90%. And further, we do have got the condenser pressure, which is 8 kPa, and the pump efficiency, which is 80%. So all the control volume conditions are known. Each component and should be analyzed and as a control volume at a steady state condition. The turbine, compressor, pump, and interconnected heat recovery steam generator operate adiabatically, and kinetic and potential energy effects are negligible, and so on and so forth. Um, Now, this is the part which actually I would definitely like. The property data given in the table below are determined using the procedure illustrated in a previous solved example of chapter number 8 and 9. The details are left as an exercise. So I would definitely say like you have to go to the each and every bit of it. You have to find the enthalpy and entropy using the methods which actually you have already learned in your previous classes. So we do have like enthalpies from state from 1 to 9, and these enthalpy should be known if you want to proceed further. Now, to determine the mass flow rate and the of the vapor and air, begin with the implying the mass and energy balancing of the HRB. So that would be mg H4 minus H5 would be mv H6 minus H7. So let's say H4 minus H5 would be there, and H6 minus H7 would be there, and that would be actually the mass and energy balance of the HRB. Now, if you go for further, you will be definitely finding the ratio of mv by mg, and that is 0.1547. So because there is nothing given about the mass of the vapor and mass of the gas, so these two are unknown. So if we have got two unknown in one equation, we cannot solve the equation. Now moving to another equation, definitely to further solve this example, uh, we do have got the gas turbine work done. So that gas turbine work done is actually work done of the turbine minus work done of the compressor, and multiply by mg. That's what actually we say. Then we do have got the work done of the vapor cycle, which is work done of the turbine minus work done of the pump. If you can check it, so something like this. So pump is from 9 to 6, turbine is from 7 to 6, 7 to 8. So that is what actually we have got, 7 to 8 and 9 to 6. So that's what actually I've said. So the combined work, the net work, is actually work of the gas and work of the vapor cycle. So net work would be something like this, adding the both the equation up there. So taking mg out, so we can have the equation which would be further something like this. Now, why we have done it? Because we know the network by the cycle, which is 45 megawatt. 45 megawatt is 45,000 kilojoule per second. We do have got this one. Putting them value in this equation, and you can find the mass flow rate of the gas and mass flow rate of the steam. So that's what actually we have got now from the two equations. Now, for the work done of the gas cycle and the work done of the steam cycle, so you can find, you have already found the mg, we have already found mv. These were known from the table. I'm sure like you would find it. um, Once you find it, that one, you can find the work done of the gas cycle, work done of the vapor cycle. Then the heat input would be from in the combustion chamber, and that is from 2 to 3, and with the mass of the gas. So that being like you can find the heat input, and once you have got the heat input, you can find the thermal efficiency of the power plant, and which come up as 52.8%, which is quite a good efficiency. Thank you very much. I hope like you understand the combined cycle power plants. I would leave the exercise which actually I've already said in these two examples to you people. If you have got any question, if you have got any problem in this exercise, you can write your question in your Google Classroom, or you can ask me anytime, and I would be able to answer that one. Thank you very much. Have a nice time.